Hello, in this lecture we will talk about function sequences and series. This is a function sequence, a set of functions enumerated by the natural numbers. Basically, we get a possibly different number sequence after fixing different x's. For each x like that, calculate the limit and set the obtained value as the value for f at x. That is how we construct the limit function f for which the sequence converges pointwise. For example, if fn is x to the n, then for each x in this interval we have a limit which is 1 at x equals 1 and 0 otherwise. We say that fn converges to f uniformly if for any epsilon we can find n such that the fn functions are epsilon close to the limit function regardless of x. Uniform convergence is very dependent on the interval, and x to the n converges uniformly for any proper sub-interval of -1, 1, but not on the entire open interval -1, 1. This is how we visualize the sequence x to the n. When considering the entire interval for any n, the continuous fn function increases from 0 to 1 closer and closer to 1, which messes up the uniformity of the convergence. This is a series of functions. For each x, we have a series of numbers. We are interested in a special case of function series, the power series, which looks like that. We usually denote capital F as the limit function of the series whenever it exists. This is familiar since we saw a few examples of Taylor expansions, and we recall that such power series converge in a symmetric interval around x null. We calculate the radius of convergence by using one of those lim sups, which are not coincidentally 1 over the term of the ratio test and 1 over the term of the root test. This calculation proves convergence on this interval, and convergence on the endpoints must be checked individually. A few important theorems guarantee that in any proper subinterval, the power series converges absolutely and uniformly. They also prove that the limit function is continuous, integrable, and differentiable inside that interval. The derivative can be obtained from taking the derivative term by term. The antiderivative can be calculated by integrating term by term. Known Taylor expansions help us to evaluate the power series. Examples. This is a convergent alternating series, but what about the limit? Recall the power series for the sine function. We would like to make use of that series, plug in x equals 1 and get the result for the series in question. We just need to verify that the radius of convergence is at least 1. So we should calculate the lim sup, which equals to the limit after eliminating all the zeros. Due to the continuity of the log function, we should calculate log of r. We use the properties of the log function to get this sum, which can be transformed into a Riemann sum of this form. The left part is a Riemann sum and contributes a bounded portion. The right part is infinity, so we conclude that the radius is infinity. You should memorize all the useful expansions and their radii instead of recalculating the radii every time. Use the handout from the basic module. Now, we can just plug in 1 and get the required value. What about this sum? That's right, plug in 2. What about this one? We cannot just plug in 4, but we can manipulate it to be the expansion of x sine x, and then plug in 2. Yes, when we have an expansion of a certain function, we can easily find the expansion of x times the function, x squared times the function, etc. Just multiply term by term. What about this one? It kinda looks like the derivative of the last one, so manipulate it to get the required form. And now take the derivative of the limit function and plug in. I hope you get the gist of these kind of problems. We need to use known expansions, and by multiplying, taking the derivatives, and integrating, we should be able to get the required form. The Taylor expansion is a constructive way to get an expansion for a specific function. This is the recipe for an. A problem that tends to find its way to the test is this. Given a function, we need to evaluate it using the Taylor expansion of a certain degree and then evaluate the error as well. The method is straightforward, and we will demonstrate it by an example. Observe this problem. In order to solve this, we should always take the derivative of all the orders up to 1 plus the required order. The extra derivative is for the error later. These are the derivatives in this case. Now, we evaluate them and build the Taylor expansion of order 2. Plugging in 1 gives us the estimation for log 2. Now for the error. The main theorem in this context gives us a formula for the actual difference between the function and the estimation. Note that we know n, we know x, and c is the only variable here, although it is bounded between x and 0. In our case, we get this formula for the error. We plug in c in the third derivative. Usually, we get a monotone function, so the extrema values are at the known endpoints of the interval for c. In our case, the term is between 1/4 and 2. So the maximal error follows. As a special case, if we treat a function as a plane curve passing through AB, the tangent line equation is the same as the linear part of the Taylor expansion. We shall see more generalized concepts in the Calc 2 module. Next time, we will take a quiz on all the material of this module.